And hello, AP Physics students. One of my favorite problems we're going to do today, the ballistic pendulum. Okay? So this is problem number 32 from chapter 7. Now, why do I like the ballistic pendulum so much? Because it uses two of the biggest ideas in all of mechanics, conservation of momentum and conservation of energy, wrapped all into the same problem. Oh, good stuff. So let's read the problem here. It says a 28-gram rifle bullet traveling at 230 meters per second buries itself into a 3-kilogram pendulum hanging on a 2.8-meter long string. Wow, that was a lot of information in one little sentence there. Okay, so here's the idea. Here's a bullet, right, traveling to the right here, right, and its initial speed is 230 meters per second, right? Okay, and it's going to hit a large object, like maybe a block of wood, and it's going to embed itself in the block of wood. And then the pendulum is going to swing back up over here. So we're told that the mass of the pendulum the mass of the bullet is 28 grams, or 0.28 kilograms. We're told that the initial velocity here of the bullet is 230 meters per second. The length L is the length of the pendulum is 2.8 meters, and the mass of the pendulum bob here is 3.6 kilograms. Okay, and the question is asking what? Let's see. What is it asking? Determine the vertical and horizontal components of the pendulum's displacement. So the bullet hits the pendulum. Both the bullet and pendulum swing up. Okay, and when it swings up, how far up does it swing? So, interesting problem, and it is a problem or a situation where I've heard that they've actually done it before to measure. They see how far the pendulum swings up, and from that, determine the speed of the bullet. Because it's pretty easy to see how far a pendulum swings up, but it's hard to get a radar gun on something moving, 500 miles an hour. Okay, so let's do a little conservation of momentum. When this bullet hits this block, we could assume there's no external forces outside the system. So the initial momentum of the system should equal the final momentum. Okay? So what is the initial momentum of the system here? Well, it's the momentum of the bullet. So we'd have the mass of the bullet times the initial velocity of the bullet here. What's the final momentum of the system? So the bullet will embed itself in the block, and then both the block and the bullet together will start moving to the right here. So what we can say here is we now have basically one object. We started with two, and we're going to end with just one. So this object would have a mass equal to the combined mass of the pendulum and the bullet, and it would have some speed v sub f, where v sub f is the speed that the pendulum's going to start moving to the right with. So if we do a little algebra here and a little bit of rearranging, we would find that the final speed would be equal to this, right? Just doing my algebra thing here. And if we plug in some numbers, we're going to get something that looks like this. And if we plug that in, we get that the final speed here is 1.78 meters per second. So the bullet comes in at 230 meters per second, lodges itself in this block, and then the bullet block system start moving to the right at 1.78 meters per second. So that was conservation of momentum. But we still haven't answered the question, right? When the pendulum, so part two of the question kind of looks like this. Okay, we start with a bullet lodged in a block like this, moving to the right, but how far does it go, right? So this would be L, and this would be L here, the length, right? How far does it go? What are the vertical, so that we'd call this H, and horizontal components of the block's displacement? Well, hey, we can figure this out with conservation of energy. This block bullet is moving to the right, and we have kinetic energy, right? So why don't we just say that the initial mechanical energy here should turn into a final mechanical energy here. There would be, assuming no air resistance or other non-conservative forces acting here. So to start out here, we would have just kinetic energy to start here, and just potential energy up here. Notice this is kind of strange. I'm saying initial energy is actually 1/2 mF squared, right? So the final of conservation momentum is the initial of conservation of energy. So our masses cancel out here, and forgot my squared. Kinetic energy squared. And I would get that H is equal to V sub I squared over 2G. And if I plug in my numbers here, that would be 1.78 squared divided by 2 times 9.8. And I would get at a height of 0.16 meters after I do some rounding. All right? So if the bullet comes in at 230 meters per second, it'll lodge in that pendulum, and then the pendulum will go up to a height of 0.16 meters. Now, at this point, we've done conservation of momentum, we've done conservation of energy, and for our last trick here, we are going to have to just do some good old trigonometry, right? Okay, so we know this is 2.8 meters. So this guy right here would be 2.8 meters minus 0.16 meters, right? So this would be 2.64 meters just from here to here. So we want to know what this guy is. So we call this X, right? The horizontal displacement. So this turns into just a good old Pythagorean theorem problem here, right? X squared plus 2.64 squared would be 2.8 squared. So little algebra there, and X would be the square root of 2.8 squared minus 2.64 squared, and we would get that X is 0.93 meters. So that would be the horizontal displacement of the bullet block system. So kind of a neat problem, pretty applicable. If you go on YouTube and do a search for ballistic pendulum, you can see some examples. But conservation of momentum and conservation of energy, the two biggest ideas in mechanics, all in one problem. Nice work, AP Physics students. Now, as your reward here, we'll get you a hilarious cartoon to watch. All right, and this is a cartoon from the internet. Oh, looks like a graph between productivity and coefficient of friction. Oh, we've all been there, right? The coefficient of friction gets larger, then less work gets done because you can't spin as much, and that's no fun. So, not sure where this part of the graph comes from because we all know a coefficient of friction can't be a negative number, right? Anyway, all right, nice work, AP Physics students. We'll see you tomorrow.